o'clock. Morning, everybody. So we're continuing our discussion of inner products this morning. And the main thing I want to talk about is this thing called the Cauchy-Schwarz inequality. And the first thing that I would like to point out is that even though I wrote the first version of these notes about 10 years ago, I only noticed this morning that I've got a T in there. There is no T in Schwarz. So, I don't know why it suddenly popped out at me this morning. Anyway, more substantively, hopefully some of you, well, hopefully all of you have probably seen this somewhere before, maybe not in full generality, maybe hopefully at least for the dot product. We're going to prove this inequality in complete generality. There's lots of nice proofs of this thing. And I'm going to give one proof that I hope is kind of nice. There's going to be another one on this week's problem set, and there'll be another one on next week's problem set. So why are there so many proofs for this thing? Because it's fundamental. And whenever we have something really important in maths, we like to have as many possible proofs for it as we can come up with. So why is this thing so fundamental? Well, one thing, it does lots of things. One thing that it does is prove the triangle inequality for the norm that we wrote down yesterday, so you can do that on the problem set too. It also has very natural interpretations in probability theory. You can interpret an inner product as the expectation of the product of two random variables, but it turns up all over the place. And particularly in analysis, it's one of the main tools that you use in analysis. Analysis is basically the business of bounding things in practice, and this is one of your key inequalities for doing that. So it turns up all over the place, and what I would like to do is try and give what is hopefully a not terribly obscure proof of this thing, because some proofs rely on, I think, not completely obvious tricks. I'm going to try and convince you that this is true for fairly natural reasons. We'll see if I succeed. Okay, so the first thing I'd like us to observe is that if one of your vectors is 0, then this thing's pretty obvious. Okay? So we'll jump in and we'll do a poll. So say the second vector is 0, then the claim is that the inner product of any other v with 0 is 0. So my question is why, right? It sounds kind of plausible, but if you take the inner product of anything with 0, you get 0. It's certainly true for the dot product. You can see immediately why it holds for the dot product, because you're just then adding up a bunch of zeros. But why is it true in general? Which axiom is it axioms is it following from? Which inner product axioms? All right, so which of these four statements is true? Is the inner product of v and 0, 0 because of positive definiteness, or because of linearity, or because of symmetry? Or do you need v equals 0 for this to be true in general? So have a think. All right, we don't have, this is supposed to hold for arbitrary inner products. We don't have a formula for the inner product. You just got to use the three properties we have specified for an inner product. Why is it true? Well, which one of these is true? So let's think about something that we said on Tuesday, I guess it was. if you fix V, and then consider this map from V to R, where T is mapping whatever you like to the inner product of V and U, that map is linear. Right? Because of the second, directly because of the second inner product axiom, that map is linear. Okay? And what do we know about linear maps? Linear maps send 0 to 0. Okay? So linearity immediately tells you the inner product of something or other with 0 has to be 0. Can't be anything else. But it's only linearity. You only need linearity to observe that. Okay? Okay, so the answer here is B. Linearity means the inner product of anything with 0 is always 0, no matter what space you're in, no matter what the inner product is. Okay, so that means if one of our vectors is 0, this will be 0. And because lengths are always non-negative, then you have a trivial inequality. Right? There's nothing actually interesting to prove. So it holds immediately in that case. Right? And in fact, in that case, it's an equality because positive definiteness of these norms over here means that if one of your vectors is 0, the left-hand side is 0, but the right-hand side is also going to be 0, and you just get 0 equals 0. So without the only interesting cases we really need to consider is when both of our U's and V's, well, U and V are both non-zero. Okay, so if one of them is 0, that way, one of them is 0, then, let me say the other one. So if V is 0, then inner product of U and 0 is 0, which is equal to then the product of the lengths, because the length of 0 is 0. That's one of our axioms. So we're going to assume both of these vectors are non-zero. Okay, so we've got two non-zero vectors. So what do we need to try and do? We need to try and come up with an inequality. And if you stare at this thing, this is not part of the proof. This is just sort of try to motivate what we're going to, the question that we actually have to try and answer. What do we want to do? Well, let's stare at what this inequality actually says. So it's got one inner product in it. It's got the inner product of U and V. And it's got another inner product in it, if you really stare at it, because the length of U is the inner product of U with itself square rooted. And the length of V is the inner product of V with itself square rooted. And if I get rid of the square roots by squaring both sides, I can get rid of the absolute values. And so I'm really looking at that inequality. Okay? Saying the square of U and V, the inner product of U and V is less than or equal to the inner product of U with itself and V with itself. Okay? So I've got three different inner products, and I want some inequality linking them. Now, what is the only inequality that we actually know that refers to, that pops out when you're using inner products? What's the only thing we actually know that's an inequality that involves inner products? Positive definiteness. That's all we have at our disposal, right? We don't know anything else about this thing. This inner product is just some map that sends pairs of vectors to the reals, and it does it by satisfying those three axioms. Okay? So if you want an inequality that looks like this, you're going to have to use positive definiteness. You don't have any choice, right? But positive definiteness involves making is an inequality talking about the inner product of something with itself. Okay? So positive definiteness looks at things that look like that, not things that look like this. So how are we going to get these sort of inner product of UV type terms popping out of positive definiteness? What kind of vectors are we going to have to apply positive definiteness to? All right, so the only inequality we have is the statement that inner product of W with itself is non-negative. So if I want to learn something like this, what kind of thing I have to choose W to be? So I'm going to want W to know about U and V, right? Somehow W has got to be some function of U and V. Now, what kind of thing can I do to U and V that will give me another vector? The only thing that I can do is take a linear combination of them, right? So W has to be some linear combination of U and V. If I want to use this inequality to get something that looks like that, the only possible thing I can do is choose W to be some linear combination of U and V. Right? There's no other possibility. Now, my claim is that it's enough to choose W to be U plus some beta V. Right? Now that's not the most general linear combination you could use. You could stick something in front of U, but it turns out that doesn't actually add anything interesting. And the reason for that is that if we're going to have U and V appearing in this thing, we can't have the coefficients in front of U and V being 0, otherwise the U or the V disappear again. Right? So we want this beta here is going to be non-zero. Now, if I stuck some constant in front of U, I would also want that to be non-zero. But then you can, since they're both non-zero, you can factor one of them out. Right? So if you put another constant in front of U, you'd want it to be non-zero. You can just factor that thing out anyway, and it doesn't actually add anything new. It just sort of rescales everything, but doesn't give you anything. Doesn't give you any additional flexibility, really. Right? What is important is to have this constant in front of V so that you can control the relationship between U and V. Right? Not their overall size, just the relationship between them. Okay? All right, so we're going to take W to be this sort of simplest possible interesting linear combination of U and V. Right? It is the simplest possible linear combination, because you've got one scalar multiple and one addition. So we just take that and we shove it into positive definiteness. Okay, so take some real number. I'm not going to assume anything about it for the time being. Right, positive definiteness implies that the inner product of U plus beta V with U plus beta V is non-negative. Okay? And now we can sort of see how we're not going to get exactly that straight away, but we'll get something that's at least got the right ingredients. Because now we can use linearity. So let's do linearity in 2 steps. So I'll keep the first argument fixed and use linearity in the second argument. So this inner product on the left-hand side is the sum of these 2 inner products. So the sum of these 2 inner products is non-negative. Right, so all I've done is simplify the left-hand side using linearity in the second argument. But we also have linearity in the first argument. So I can do the same thing now. So I'll do it to this one and then separately to this one. So linearity in the first argument acting on this thing is inner product, or gives me inner product of u with itself, plus beta times inner product of v and u. And now we'll work on this guy. So we've got beta times inner product of u with v. Right, that was that beta just sitting out the front. Plus, now I've got beta times the inner product of v with v. So I've got a beta squared inner product of v with v. Okay? Now, what do I know about these two terms? They're the same, right? They're equal because of symmetry. So I've started with positive definiteness, then we used linearity in both arguments, which actually involves symmetry as well. Now I can use symmetry one more time. So what I really have is that the inner product of u with u plus twice beta inner product of, say, u with v plus beta squared inner product with v is non-negative. Okay? All right. So this is sort of looking closer to this. Still a long way off, but it's sort of looking closer because what I've got is precisely the three ingredients that I want. This thing and this thing. Okay? We've got the three ingredients that we want. So now, and the good news is that this holds for all beta. So the game now is sort of choosing the best possible beta that will make this inequality as interesting as possible. Okay, so let me start off by taking, say, this guy over to the right-hand side. And I'll get a minus sign in front of it. And we end up with this statement. Okay, is everybody with me so far? Yep. So you mean this one? So this is just linearity. Okay, so it's linearity in the second argument. So you keep the first one fixed, right? The first one is staying u plus beta v. That's just some vector. Okay, so it's just linearity in the second argument, and I'm just playing with the left-hand side, right? So these two statements here on the left-hand side, they're equal. Okay, so if one of them's greater than or equal to 0, the other one's greater than or equal to 0 because they're equal. So the definition is, so you've always got two arguments in the inner product. The definition is that you need to be linear in the second one, right? But you're also symmetric, so you can just swap the first and the second around. And then, so that immediately implies you're actually also linear in the first argument. Okay? So you can do it to either. I'm just sort of doing it to one at a time here to keep things clear. Okay? So this step is linearity in the second argument. This step is then linearity in the first argument. So you've got linearity in both, and we're just doing it one at a time. So let me call this thing equation star. All right, any other questions? Everybody sort of comfortable with how we got to star? Okay, so you just take an arbitrary linear combination, simplest possible linear combination of your two vectors that you want to prove Cauchy-Schwarz for, and you shove them into positive definiteness, and you shuffle stuff around a bit, and you get there. Okay? So no super crazy tricks thus far. All right, now, what part of the real line does the right-hand side live in? Yeah, right? The right-hand side, in fact, it's even better than that. The right-hand side is strictly positive because u and v, we assumed, weren't 0. So positive definiteness tells, if you just stare at the right-hand side, those two inner products on the right-hand side, they're both strictly positive, and beta squared, I mean, I guess it could be, beta could be 0, although that wouldn't be interesting, and it's not going to help us. So beta, you also know, is going to be non-zero if this is going to work, otherwise you're turning off the v term and you're definitely not going to get Cauchy-Schwarz. But regardless, the right-hand side is definitely strictly positive. So unless we make sure the left-hand side is also, positive, we've got a completely uninteresting inequality, right? If the inequality you derive says something negative is less than or equal to something positive, you haven't done anything useful at all, right? Because you knew that before you started. So we need to choose beta in such a way that the left-hand side is actually positive, or at least non-negative. Otherwise, we haven't done anything. So how do we choose beta to guarantee the left-hand side is at least non-negative? Yep. You could let it be -1, but what happens if the inner product of u and v is negative?
Beta is a non-zero negative part, just any non-negative number.
So we can choose, the answer really depends on what the inner product of u and v looks like, right? So the inner product of u and v could be negative, it could be positive, it could be 0. We don't actually know. Right? We know the inner product of u with itself is positive and v with itself is positive, but we don't know anything about the inner product of u and v. So we've actually got to consider two cases separately. And we're going to choose beta slightly differently depending on whether the inner product of u and v is negative or not. Okay? And that's fine because we're allowed to choose beta to be whatever we want because this inequality holds for all beta. Okay? So the idea is you sort of fix the pair of vectors you're interested in, and then you choose a beta that tells you the most information you can possibly squeeze out of it about the inner products of those two vectors. Okay? All right. So the right hand, let me actually copy this down. So we can stare at it. Okay. So the right-hand side is positive. So if the inner product of u and v is, say, non-negative, then the inequality we've derived is completely trivial if minus beta is not positive, right? We need minus beta to be positive for this to be anything interesting. So let's say lambda is minus beta and it's positive. Okay, so I'm just giving a new name to minus beta, it's lambda, and lambda's positive. So what do I get? We get 2 lambda inner product of u and v. It's less than or equal to u minus lambda squared times the inner product of v with v. But minus lambda squared is the same as lambda squared. So the right-hand side doesn't care about this. Okay? And now let's remember what we've got in the Cauchy-Schwarz inequality. In the Cauchy-Schwarz inequality, we've actually got absolute value signs there. Now, why can I get away with writing those here? because I'm assuming that the inner product of u and v is non-negative, right? So it's equal to its absolute value. So we can just shove in the absolute value signs if you like at this point. Okay? We're not cheating because we know that thing's non-negative. And because lambda is strictly positive, I can divide by it. And I'm now getting even closer. I've really got all three ingredients that I had in Cauchy-Schwarz. Constants are kind of a little bit wrong. And on the right-hand side, I'm not multiplying these two things together. I'm adding some linear combination of them, which seems a bit strange. But we'll come back and think about that in a minute. But it seems like some kind of progress. But we've completely ignored the case when the inner product of u and v is negative. So let's go back and think about what happens in that case. And it's similar, but you've got to choose beta a little bit different. Okay, so if the inner product of u and v is negative, then when is this thing trivial? So if inner product of u and v is negative, then minus inner product of u and v is positive, right? So I would have beta times something positive on the left-hand side. So this is going to be a useless inequality if I choose beta to be negative, because then I'm back in the realm of having something negative being less than or equal to something we know is positive, which is pointless. Okay? So in this case, because minus inner product times u with v is positive, I need beta to be positive. So in this case, our inequality is trivial unless beta is positive. Okay, so when beta is not positive, it's completely trivial. Now, that means we're going to choose beta to be, or lambda to be some, well, beta to be lambda, which we're taking to be strictly positive. Okay, let me write it the other way around. Might make more sense. So beta is now lambda, but before beta was minus lambda. But lambda, again, we want to be strictly positive. Now, if this holds, what is this? Right? I know it's positive, but what is it? If you got, you know x is positive, right? And you look at minus x. What's minus, sorry. If x is negative and you look at minus x, what are you really looking at? It's a positive number, but it's the magnitude of x, right? If you've got the absolute value of a negative x is just minus x. The absolute value of a positive x is just x, but the absolute value of a negative x is minus x. So since inner product of u and v is negative, minus inner product of u and v is absolute value of inner product of u with v. Okay? So we go back and look at star. This minus sign sitting here is great because it just combines with the inner product of u and v and gives me absolute value of u and v. So in this case, what do we get? We get 2 lambda inner product of u with v less than or equal to u, inner product of u with u, plus lambda squared, inner product with v. And so we get exactly the same thing. All right, you can divide through this thing by lambda again, and we get exactly the same thing. We get 2 times, that should be absolute value, 2 times the inner product of u with v, its absolute value is less than or equal to inner product of u with u, plus, whoops, lost a 1 on lambda, plus lambda times inner product of v with v. Okay. So we'll call that equation double star, and that holds for all positive lambda, and it holds no matter what the inner product of u and v looks like. Could be negative, could be positive, could be 0, don't care. This holds for all choices of u and v other than 0, and it holds for all, we don't need to consider those cases because we've already considered them, and for all positive lambda. So now we've got this inequality that has all the right ingredients in it to hopefully produce the Cauchy-Schwarz inequality. But in fact, we haven't just got one inequality, we've got infinitely many inequalities. Because if I choose lambda to be 7, I've got an inequality. And if I choose it to be 43, I've got another inequality. And so the question is, how should I choose lambda to get the best inequality? And so what would we mean by the best inequality? If you've got these infinitely many inequalities, one for every lambda, what does it mean to pick the best one?
The smallest.
So what has to be the smallest?
You choose like the smallest lambda you use.
So it doesn't necessarily need to be the smallest lambda, because if I make lambda as small as possible, what's going to happen? This term's going to blow up. And if I make lambda as big as possible, this term's going to blow up.
Match the left side. We match the left side too.
So in principle, that would be great, but it's probably going to be false in general. Sometimes the left-hand side is actually strictly less than the right-hand side, but you want to get it to be as close as possible.
So choose the right-hand side to its smallest value.
Yeah, right? So you want to look at the right-hand side as a function of lambda and say, what's the value of lambda that makes that right-hand side as small as possible? Because if you've got one inequality that says x is less than 3 billion, that might be kind of useful, but it's not as good as one that says x is less than 10, right? They can be both true at the same time, but saying x is less than 10 is a lot more useful than saying it's less than 3 billion. So you want to, since you've got an inequality for every single lambda, you want to choose lambda to make the right-hand side as small as possible so that you get the strongest inequality, right? The inequality with the most information in it. And so actually it won't be a question of making lambda as small as possible or lambda as big as possible. It'll be sort of this balancing point that makes the whole thing as small as possible. Okay, so that's a good time for another poll. If I can get my phone to work. So how do you do this? Right, that's the inequality we've got. How do you pick lambda to get the best inequality? All right, and I'm helping you out. Here's 4 possibilities. And how would you actually prove it? And my advice here is consider u and v to just be fixed, right? So the inner product of u in itself is just something fixed, and the inner product of v with itself is just something fixed. And so what you've got is this function of lambda, and you want to choose lambda to make that function as small as possible. And it sounds like the kind of thing that you do in calculus. So how do you actually do it? You might want to grab a pen and a bit of paper and just do a little calculation. Right? So don't be put off by all the abstract stuff. This is just something on lambda plus something else times lambda, and you want to pick lambda to make that as small as possible. Okay. All right, I'll give you a clue. The answer is not 1. If you answered 1, I think that's just because you couldn't be bothered doing the calculation. So actually try and have a crack at it. It's not 1. So let me suggest you look at this function. Right, this is what we're really looking at. Some f, the maps from positive lambdas to this thing. And for us, A is inner product of u with itself, and B is the inner product of v with itself, but who cares, right? They're just some fixed coefficients, so you've got a function of lambda. So where does that thing take its smallest value? All right, so I would take the derivative. I set the derivative to 0, right? That's how you find turning points. And if you do that, what do you get? So you find this has a minimum at lambda equals a on b rooted. Okay? So in our case, a is inner product of u with itself, or length squared. So I guess one thing that I could observe here is that the inner product of, let's put the lengths in now, the squared lengths. This is really inner product of length squared of u. This is really length squared of v. So A is length squared of u, and B is length squared of v. We want the length squared of u up top, the length squared of v down below. We want to square root that. That gets rid of the squares. So we just want the length of u on the length of v. So it's C, right? That's going to be the best choice of lambda. Now, what's one nice thing about this choice of lambda? What does it do to the right-hand side? Yeah, it makes them exactly the same size. Okay? So the choice of lambda that you need is precisely to balance these two terms. If you make lambda too small, the first term's too big. If you make lambda too big, the second term's too big. You choose lambda in this way, it makes them exactly the same size. Okay? And if we do that, what do we get? Twice the inner product, absolute value of inner product of u with v. Length squared of u. Length of v on length of u, because this was 1 on lambda, plus length of u on v. And you get precisely twice length of u, length of v. And now the hardest part of the whole calculation is you get to cancel 2's. Okay? So we've got Cauchy-Schwarz. So it's still I agree, not the most direct proof of anything you've probably ever seen, but hopefully that's a minimally tricky proof of Cauchy-Schwarz, okay? It is quite natural if you look at it the right way. Okay, any questions? All right, good. So let's look at some consequences. So the first is that if you now divide by the length of u and the length of v, so assume u and v are non-zero, then you find that the inner product of u and v divided by the length of u divided by the length of v, that lies strictly between -1 and 1. Now, why is that useful? Well, in Rn with the dot product, that's precisely how we define angle, right? We say the cosine of the angle between two vectors is precisely this thing. And if you want to be able to generalize that to this abstract setting, you need this inequality here to hold. Right? Otherwise, you can't do it. We wouldn't be able to define angle in the same way. So we can define angle in the same way in any arbitrary inner product space as we do in Euclidean space, precisely because of the Cauchy-Schwarz inequality. Okay? So Cauchy-Schwarz allows us to define angles. Okay? So we say the angle between two vectors is the arc cos of this thingy that's basically left-hand side divided by right-hand side of Cauchy-Schwarz. Okay? Now, you can't really do that if u or v are 0, but if u or v are 0, then you don't actually need to. But it doesn't really make much sense. But if u and v, it's sort of ill-defined what the angle between some vector and the 0 vector is. But for non-zero vectors, this makes perfect sense now. And the reason this works is because arc cos is now only invoked on its domain. So we can, given this notion of an angle, we can now ask questions like, what's the angle between sine and cos, right? So we've already looked at what the length of sine was, etc. But now we can ask the question, what's the angle between sine and cos? And this isn't sort of a direct definition of angle in the sense of, right, you draw something in the plane and you can get your protractor out, right? You can't measure this with a protractor, but it's a well-defined thing. And we know we're going to need the inner product of sine with itself, right? Because we're going to try and shove it into this formula. So we want to compute this integral, right? Because that's the inner product that we were using. And if you remember your double angle formula, this is integral of sine 2x on 2 dx. And if you just crunch that out, you get 0. So theta is arc cos of 0, and that's pi on 2. Okay? So in this well-defined sense, the angle between sine and cosine is pi on 2. So if you translate that back into Euclidean space, what did it mean when you got two vectors that have got angle pi on 2? They're perpendicular, right? They're at right angles. So with respect to this inner product, sine and cosine are at right angles to each other. And hopefully you've seen this idea before. So when this happens, we say those two things are orthogonal. Okay? So sine and cosine are orthogonal with respect to this sort of standard inner product on function space, continuous function space. And because of our definition of angle, in any inner product space, two vectors are going to be orthogonal, right, if and only if their inner product is 0. Okay, so having angle pi on 2 is the same as having inner product 0. So we don't actually need to compute arc causes and stuff. You just look whether or not the inner product of your two vectors is 0. So that's the definition of orthogonality. You've, I'm sure, seen it in Euclidean space, but it works in any inner product space. So what we just showed in the previous example is that sine and cos are orthogonal. Okay? But it's worth pointing out that that's only with respect to the given inner product. Right? You pick a different inner product, different vectors are going to be orthogonal to each other. So orthogonality is dependent on your choice of the inner product. All right, let's see one more poll. Whoops, not that one. This one. Okay. So, true or false? If you've got two vectors in a product space and they're independent, then they're orthogonal. All right. Two independent vectors. This is sort of asking for the relationship between independence and orthogonality. If you've got two independent vectors, are they orthogonal? So you can answer this by thinking of some very familiar case, right? So you sit in R2 and use the dot product. And picture two, the sort of question is, can you think of two independent vectors that aren't orthogonal? If you sit in that setting, and the answer is sure. Right? If I sit in R2, that guy and that guy are independent, because one's not a multiple of the other, but they're not orthogonal, because the angle between them's something that's not pi on 2. Right? And if you want a more concrete version of the answer than that picture, say you take 1, 1 and 1, 0. And then note that these two things are definitely independent, but they're definitely not orthogonal. Right? V dot u is 1. It's not 0, but neither is a multiple of the other, so they are independent. Okay? So this is definitely false. But we will find later that if you've got two vectors that are orthogonal, as long as neither of them 0, they are independent. Okay, so there is a link between independence and orthogonality, but it's not the simple one given in that poll. All right, let's look at a couple more examples. So just to emphasize that orthogonality depends on which inner product you're talking about. If you take those two vectors, you sit in Euclidean space, and they are orthogonal, right? Because u dot v is 0. But if you use this inner product, then the answer is no. Why is it no? Because if you take the inner product of u and v in this case, what do you get? You get 3 minus 2, which is 1, which is not 0. Okay? So the question of whether two vectors are orthogonal depends on the choice of the inner product. So it's a question that is only well posed in a given inner product space, not in a given vector space. In a vector space, you can say, are these two things independent? You can't ask in a vector space whether two things are orthogonal. You need to specify which inner product you're talking about, and the answer will change depending on which inner product you're talking about. Okay. one final thing, and then we'll wrap up for the week. A much easier thing to prove is a generalization of the Pythagorean theorem, Pythagoras' theorem. You can do this. You're all familiar with this in like R2 and R3 with the dot product, but it works in any inner product space, and it just says that if you've got two vectors and they're orthogonal, then the squared length of the sum is the sum of the squared lengths. And this is a very simple thing to prove. So the squared length of anything is just the inner product of that thing with itself. So you simplify this out using linearity in the same way that we did in Cauchy-Schwarz. So I'm using linearity in both arguments all in one step here because it's the same as Cauchy-Schwarz. But this thing's 0 and this thing's 0 because they're orthogonal. And this first term is the squared length of u, and the last term is the squared length of v. And so you're done. Okay? So this is called triangle inequality because in, say, R2, you get these little arrow pictures indoctrinated into you in specialist maths, right? It looks like a triangle because u and v are orthogonal at right angles, but same idea holds in any inner product space. Okay? Sorry, not the triangle inequality. This is the Pythagoras' theorem. Triangle inequality is similar-ish, but you actually need Cauchy-Schwarz, and you can prove that on the problem set. Okay. All right. That is, I reckon, enough for the week. The only other thing that I'll mention is you can read ahead, and everything that we defined about orthogonal complements, etc., holds in these abstract inner product spaces, right? So all that stuff about